So in our discussion of differential equations to this point, we've talked about how to solve differential equations through algebraically by separating the variables. And when we can't solve a differential equation algebraically, we've looked at how to approximate or visualize the solution through the use of slope fields. Now there is a third way that you can use to estimate a solution, and that's a numerical approach called Euler's method. So to show you what Euler's method is all about, I'm going to use this demonstration from the Wolfram Alpha project website. And I have a differential equation here, y prime equals x squared minus y. One of the solutions to this differential equation is shown in blue, the blue curve. Remember, a differential equation has a whole family of solutions. This is one solution, a particular solution with a known starting point of 0, 2. This differential equation, by the way, is not one that we could solve algebraically through separation of variables. We'd have to use some much more advanced methods beyond the scope of this course. So all we're going to do here is show a way to approximate it using Euler's method. So to begin Euler's method, what we do is we take our starting point and we draw a tangent line at that point, or we think of a tangent line at that point. So at 0, 2, I could certainly calculate the slope of the tangent simply by plugging 0 and 2 into the derivative, and doing that would give me a slope of -2. And so the idea here is to draw the tangent line and follow it for a given horizontal distance. I'm going to follow it from 0 to 4, and when I get down here I could calculate this y value, which is actually -6. It's not quite lighting up here, and that y value on the tangent line is said to be my estimate for the real y value on the solution. Now I know you're thinking, well, gee, those are quite far away. That's not a very good approximation. And you're right. And of course, the reason for that is that the tangent line and the curve are only close to one another at points close to the point of tangency. We're way far away from the point of tangency. All right, so to give ourselves a better estimate, what we're going to do is we're going to break this interval up into multiple tangents. And I'm going to, instead of using one big interval of length 4, which we call the step value, step 4, I'm going to break it into 2 steps of length 2 each. So I'm going to change this. And so what's happening here is we still have our initial tangent line, which we're going to follow, but we're only going to follow it for a horizontal distance of 2. Now the y value here is -2. Alright? So the idea is that we're going to put in a new tangent line here using the updated slope at this new approximation point. So 2, -2 is our approximation of the curve at this point, which again is still not very good. And we're going to use that to calculate what the slope of the tangent would be at that point on the curve. We can simply plug in 2 for x and -2 for y, and that would give us a slope of 6. And we could then draw a line with slope 6, take our old y value of 2, do a slope of 6, up 6 over 1. Okay, that's 1 unit, and now we have to do it for 2 units since we're following the interval for 2 units. Another up 6 over 1, and we get an estimate here of 10. Which looks like it's the actual solution to the curve, but we're not completely sure about that. But the point is, we got a better estimate than we had before. So the idea of Euler's method is to start with your known point, calculate the slope of the tangent at that point, find the change in y to get to the next y value. This y value becomes our new estimate. We then calculate the slope at this point, find our change in y to get to our new y value, which is now our next estimate. So the whole concept of Euler's method is that our new estimate, our new y value, is found by taking our original y value and applying the change in y, which is determined by the slope and the distance that we're traveling. And to be more specific, this is the rate, the slope, which is the rate per 1 unit times the number of units we're traveling, which is the change in x. This is the concept of Euler's method. Alright, let's just lay out numerically what exactly I just talked about with the visualization. And I like to do this by using a chart. So what we were just talking about with the animation was approximating y of 4 using a step size of 2, which is my change in x, knowing that I'm starting at the point 0, 2. Alright, so I like to lay this out in a table, as I said. My first thing that I'm starting with, my starting point is, in this case, 0, 2. To calculate my change in y, I need to know what the rate is. That's key. And the rate is the derivative. Once I get my rate, I need to multiply that by the change in x to get my change in y. So change in y is in this column, which is the rate times delta x. And that is then able to bring me to my new point. So I'm at 0, 2. And if I plug 0 and 2 into the derivative for x and y, I get my rate to be negative 2. So my slope is negative 2 here, and I'm going to follow the negative 2 down 2 over 1 for, in this case, 2 units. So my change in y is going to be negative 2 times over 2 units. 2 is negative 4. And that's going to make my new point. My x value is changing from 0. It's going up by 2 every time. And my y value is going up by negative 4, or down in this case. So I land at 2, negative 2, which, remember, was our first point along the way to our final approximation. 2, negative 2 right there. Alright, our new point then becomes our starting point for the next step in the process. So if I plug 2, negative 2 into the derivative, I get 4 minus negative 2, I get a rate of 6. I'm going to follow the rate of 6 for 2 units, so that's going to give me a total change in y of 12. And so my new point, estimate, which is going to be my final stopping point, because we're going to be at 4 now, is 4, comma, the y value is changing by 12 units to 10. And so we're saying that y of 4 is approximately 10 using Euler's method, which is precisely what you see on our animation. Now I could continue doing this process with smaller and smaller intervals. So if I did this with 4 intervals, so I get 4 tangent lines, starting y, add the change in y to get my new y, starting point, add the change in y to get my new y, do this over and over again, you'll notice that as I make the intervals smaller and smaller, that all of my little tangent lines put together, all my linearizations as we call it, get closer and closer to what the actual solution is. Remember that you use Euler's method to approximate the solution to a differential equation. We wouldn't actually know that the solution was the blue curve unless we were able to do this algebraically. But through Euler's method, we can get a pretty good estimate, what you see in purple, to what the actual curve is by taking smaller and smaller intervals. So just to reinforce this concept, what I'm going to do is I'm going to do an approximation of y of 4 again, this time using 8 sub-intervals. And that would therefore mean, since I'm going from 0 to 4, my delta x is going to be a half a unit. Alright, so same question. The only thing that's changing this time is that my step size is 0.5. My starting point is still the same, and my differential equation is still the same. So we have our point, our rate, our change in y, and our new point. So we're starting with 0, 2. Plugging that in, we get our rate of negative 2. We're following a slope of negative 2 for only half a unit, so my actual change in y is only negative 1. And so my original point 0, 2 has increased by half a unit to 0.5, and my y has gone down 1 unit from 2 to 1. So that's my estimate so far. First estimate right there, a half, 1. Looks correct on the animation. Take our next point, and now we're going to plug in our slope here. So we're going to have a half squared, which is a quarter, minus 1, which is negative 3/4. And we're going to take our rate and follow it for half a unit, which is negative 3/8. And so my new point is x goes up by a half to 1, and the y, we add our change in y, negative 3 over 8, which lands us at 5/8. Continue the process again. So it's the same process over and over. Okay, if you're a computer, you would love this because you could whip through this very quickly. Okay, and you could do many approximations. We're going to just do one more here, and then I'm going to use technology to bring us up to our estimation. So 1 comma 5/8, again, plugging in our points into the derivative, we would have 1 squared minus 5/8, which would be 3/8. Our change in y would be 3/8 for only half a unit, which is 3/16. And so our new estimate, increase x by a half, change y by 3/16. So that would be 10/16 plus 3/16, 13/16. Okay, and that then becomes our next point. And this process goes on and on and on until eventually we get down to 4 comma something. And there are lots of programs out there that you can use. Here's one that I've got on my calculator. In y1, I'm typing in my differential equation, which is x squared minus y. And then my program, my Euler program, I'm going to run it. I need to provide my starting x, which was 0, my starting y, which is 2, and my step size, which was 0.5. And every time I press the button now, I'm going to get the estimates one by one along the way. Okay, so my first is 0.5 and 1, which is this one right here. Enter. The next one is 1 and 0.625, which is this one. Third one, 1.5 and 13/16 is what that is. And so I can keep going along the way. X equals 2, x equals 2.5, x equals 3, x equals 3.5, x equals 4. My y value is approximately 9.502. So y of 4 is approximately 9.502, which on my animation is right there, and you can see the y value there. That y value, the decimal is what we just calculated, 9.502. So just to conclude, Euler's method is this concept, and just to show you how you'll often see it written, the derivative we're going to express as a function of its own in terms of x and y. It could be just in terms of x or just in terms of y, but we'll use that notation. And so Euler's method is saying that our approximation of y, our nth approximation of y along our steps, is based on our previous estimation, n minus 1, plus our rate, which we're using this, remember, f at the previous point, times our change in x, where our starting point and change in x are given.